Look at your phone, your laptop, the cloud running this video. Now imagine this. Every one of those machines exists because humans learned how to control electrons inside a piece of sand. A grain of sand. Something so small it slips through your fingers, yet powerful enough to run civilizations. Inside that grain lies silicon, the foundation of every smartphone, every data center, every satellite, every AI model, every medical scanner, every modern weapon system. Our world no longer runs on oil, it runs on chips. But here's the part that nobody sees. The future of those chips is not decided when a company announces 2 nanometers on stage. It's not decided in Silicon Valley, not in Taiwan, not inside trillion-dollar corporations. It's decided years earlier, quietly inside a research campus in Leuven, Belgium. This is the story of IMEC, the most influential semiconductor organization you probably ever heard of. The year was 1984. IBM launched the personal computer. Apple introduced the Macintosh. Microelectronics was about to reshape humanity. At the same time, Belgium, a country with no major semiconductor company, made a radical decision. Instead of creating a national chip champion, they created something far more powerful, a neutral laboratory. IMEC, the Inter-University Microelectronics Center, was founded on a non-profit research institute spun out of KU Leuven. It began with just 70 researchers. The mission was bold and almost reckless. Work 3 to 10 years ahead of industry, solve problems before any company even realized they exist, and share the risk across the entire ecosystem. That decision quietly rewired how semiconductor industry innovates. Here's a reality that almost sounds unbelievable. Intel, TSMC, Samsung. These companies fight like enemies. They race nodes, they guard secrets, they sue each other, and yet, they all pour billions of dollars into the same place. And that place is IMEC. Why? Because IMEC is completely neutral. IMEC does not build commercial chips. It does not sell processors, it does not compete with anybody. IMEC cannot win the race because it's not running in one. And that's exactly why the entire semiconductor industry trusts it. Modern chip R&D has become brutally expensive. A single wrong decision at an advanced node can cost tens of billions of dollars, years of lost time, or even a company's survival. At sub-5 nanometer, you're no longer just engineering, you're fighting physics itself. So instead of gambling alone, competitors do something radical. They share the early risk. At IMEC, companies collaborate on fundamental R&D like the future transistor architectures, lithography challenges, materials and interconnect limits, power delivery and scaling walls. Not products, not secret designs, but just the physics problems everyone must solve. And the money proves it. More than 75% of IMEC's €1 billion annual budget comes directly from the industry. Intel, TSMC, Samsung, ASML, Micron, Nvidia, Apple, they don't donate, they invest because IMEC gives them something that's priceless. Answers before it's too late. IMEC runs the world's most advanced independent semiconductor R&D pilot line, built with over $5 billion in long-term investment. This is how IMEC quietly aligns the entire semiconductor industry, material suppliers, tool vendors, foundries, and even designers around a shared future roadmap. As IMEC CEO Luc van den Hove puts it, the risk of getting advanced technology wrong is now too large for any single company. That neutrality is IMEC's superpower. That's why the industry calls IMEC the Switzerland of semiconductors. If IMEC had one defining achievement, it is this: extreme ultraviolet lithography, EUV. To print smaller transistors, you need shorter wavelengths of light. EUV uses 13.5 nanometer light that is absorbed by air, forcing the entire process into vacuum. It requires atomic scale mirrors with near perfect alignment and machines costing nearly $500 million each. ASML builds these machines, but IMEC makes them usable. Years before EUV tools even existed, IMEC tested EUV photoresists using synchrotron radiation in Switzerland. They developed early EUV optics and process flows and aligned mask makers, material suppliers, and tool vendors. When ASML shipped its first EUV alpha tool in 2006, IMEC was among its very first recipients. As former ASML CTO Martin van den Brink later said, high-NA EUV wouldn't exist without IMEC's long-term partnership and early mask research. This wasn't luck. It was decades of coordinated engineering centered at IMEC. Here's something most people don't realize. When you hear about a breakthrough chip today, you're often seeing ideas that IMEC explored 5 to 10 years earlier. FinFETs researched and optimized at IMEC before mass adoption. Gate-all-around nanosheets were prototyped at IMEC long before foundries even used them. Backside power delivery was demonstrated in IMEC pilot lines years before public announcement. Chiplets and 3D integration were studied while the whole industry was still obsessed over monolithic SoCs. Even today's AI hardware trends, in-memory compute, analog AI, photonics, were first stress tested inside IMEC labs. As Intel CEO Pat Gelsinger put it, IMEC is the global lighthouse guiding the industry beyond Moore's Law, one node ahead, 1 decade early. IMEC doesn't predict the future, it builds test versions of it, and the whole industry decides whether it survives. As traditional scaling slowed, many believed Moore's Law was dead. IMEC disagreed. Instead of chasing smaller dimension, IMEC reframed the problem. They focused on system technology co-optimization, 3D integration, entirely new transistor architectures. That led to one of the most radical ideas yet. CFET, complementary field effect transistors. Instead of placing NMOS and PMOS side by side, CFET stacked them vertically. This removes spacing from the equation entirely. IMEC explored two paths, monolithic CFETs and sequential CFETs, using innovations like self-aligned gate merging, low-temperature wafer bonding, smart cut layer transfer. IMEC showed that sequential CFETs can approach monolithic performance. That insight may define logic scaling beyond 1 nanometer. Semiconductors are now geopolitical weapons. Export controls, CHIP Act, national security. IMEC sits at the center of this storm. Its position is clear. Collaboration beats duplication, coordination beats isolation. IMEC voluntarily aligns with US export control, while remaining neutral among trusted partners. Under the EU CHIPS Act and US CHIPS Act, IMEC expands pilot lines, partners with Purdue, MIT, Michigan, and New York, avoids rebuilding identical infrastructure everywhere. IMEC is also a talent factory. At any moment, 850 PhD researchers on site, hundreds of university collaborations worldwide. IMEC has incubated 300 plus startups, created 130 plus spin-offs, enabled nearly 1 billion euros in following funding. As IBM Mukesh Kerr once said, if you want to build the next transistor, you gotta go to Leuven. IMEC doesn't ship chips, it doesn't chase headlines, it doesn't sell products. Yet nearly every advanced chip on Earth carries its fingerprint. From EUV to CFETs to AI accelerators to quantum control. IMEC proves something profound. The future isn't built by the loudest players, it's built by those who quietly make progress possible, one grain of sand at a